This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So how I would suggest that we run this is that we have the test for this 30 minutes. If you finish early and want to leave, that's all right. Just come back after the time. Maybe we just take a break after that, after the test. That's acceptable to everyone. So if you do leave early, then just make sure you're back by 6, so the latest. Continue. And we can negotiate over whether we have another break later. Okay, does anyone need more reading time or all set to go? More reading time, okay. It's obviously closed book, so any notes off your desk. Just use it when you Okay, so first thing you do, of course, is write your student number at the top. If you don't have that, then I'm stuffed. So let's get going. think 29 hours will be long enough. Sorry about that. question 3, make sure you interpret the result. Don't just calculate a distance. It says, what's the minimum distance from which you would have to view the Apple iPad to be able to see the difference between standard deviation and high definition? So make sure you answer that question. Not just give calculate some distance. break. Now the pressure's on. And maybe 5 minutes.
Question. I only just thought of it then. The very last question. Asked kind of minimum distance. Should it be the maximum distance? Required to notice the difference between SD and HD. Because basically, you can just keep getting smaller and smaller, and you still notice the difference, right? So even if you hold it directly in front of your face, you'd still be able to see the difference between SD and HD. But if you go past a certain point far away, then you wouldn't be able to see the difference.
Yes, you're right, actually. Yeah, okay.
I thought I was going crazy.
No, sorry. Yeah, you're right. Okay. Okay, so any comments anyone wants to make about that wonderful test? How much fun it was? No, okay. All right, so let's continue with where we were up to, and you'll recall that I was giving you a bit of a combination of a history lesson and a technology discussion about the various MPEG coders, and we got up to about here. And MPEG-4 is a little bit confusing, and the reason it's confusing is, or the reasons it is confusing, first of all, it was much more than just a video and audio coding solution as the earlier ones had been. So there were all these other things that they were trying to build into it, the ability to do object-based representation, that is coding the objects in a scene separately, including all sorts of other media such as the graphics and the text and synthetic objects, so like MIDI music, vector-based graphics and so on. So, so as well as just the video and audio components, and we'll get on to audio next week, by the way, they were trying to do all these other things. Then it's additionally confusing because they did include a new video coding solution, which became known as MPEG-4 Part 2, but in comparison with what else was happening at the time, it wasn't all that impressive. It didn't give a significant improvement in performance that would make you use it rather than something that already existed. So a couple of features in it worth noting are that the motion estimation went down to quarter pixel instead of half pixel, so the sub-pixel motion estimation was taken that extra to that extra granularity, and they also included a global motion compensation feature. So if you could detect that the camera was panning, or for whatever reason the scene as a whole was moving past the field of view, then you could estimate a single motion vector which would compensate for that, and then that would hopefully reduce the size and range of motion vectors for the individual blocks within the picture. But in the end, as I say, the performance wasn't all that great. And from the historical point of view, they were developing this standard around the same time as the ITU group, the competing group, if you like, had developed a significantly improved coding system, which was H.264, also known as advanced video coding. Yeah, that's the other confusing thing about these systems, is they often end up with more than one one name. So we'll talk briefly about H.264 and the next generation H.265, but I don't want to go too much into the detailed tools. I'll rather take a high-level look at what at the approach that they took, and this will hopefully make more sense in a couple of minutes. So H.264, which also became known as MPEG-4 Part 10, so it's published in both standards, was an attempt to make a significant increase in coding efficiency, and it achieved that, but at a price in terms of complexity, and we'll talk more about complexity over the next couple of slides. And the basic approach that was used was a lot of adaptivity. So instead of having fixed block sizes, for instance, it allowed for flexible block sizes. But if you allow for flexible block sizes, it means you have to include some decision making about what size to use. And an awful lot of prediction. So that's actually a quote from a colleague of mine who used to work for a company that was implementing it for TV applications, and that was his summary to me. Anything that can be predicted is, basically. So again, I'm not expecting you to memorize the features in these things, but just a bit of a feel for some of the technologies or some of the approaches that are used within this H.264. Large number of reference frames, up to 32 reference frames could be used for motion compensation. There were so that it comprised of a a short-term store of the recent pictures, so recent pictures that have been coded would automatically go into to some of these reference pictures, but also you could manually store, so you could label some frames as being suitable to put in this store and therefore available for motion compensation later. But of course, all of this flexibility sounds very good. If you have the ability to store any number of frames or a selection of frames in these reference picture collections, then it can only improve your possibility or your likelihood of being able to do good predictions and therefore reduce the bit rate. But how do you test all these options to decide which pictures go into this manual store? Up to H.264, and as we have discussed earlier, B pictures were never used to predict other pictures, but this was this condition was lifted at this point. So again, just providing flexibility. If you want to predict other B pictures from some B pictures, then you can do it. I mentioned an adaptive block size, so instead of being locked on into 16 by 16, it could come down to 4 by 4. We'll talk about that in a second. 8 by 8 transform sizes had been used previously, but they allowed for 4 by 4. Quarter pixel motion compensation. They allowed for a weighted prediction for motion compensation. Remember I talked about the fade problem that emerged from MPEG-2. No one had tested fades, and motion compensation basically didn't work. So they allowed for the possibility of using a motion vector and then just scaling the prediction to allow you to predict fades. The intra prediction we'll talk about in a separate slide, so I won't confuse you by trying to introduce it without the graphics. Instead of having the groups of macro blocks all contiguous, it allowed for them to be distributed throughout the picture. So this meant that if you lost one of these groups, at least the error was not so noticeable because it was all concentrated in one part. You could spread the effect and maybe even hide it in some way. And they introduced a particularly effective form of arithmetic coding to encode all the code words in the end before transmission. H.265, the next generation after that, also called high efficiency video coding, is pretty much the most advanced one that is widespread used today. Yet again, it was a joint MPEG ITU initiative. Even more prediction modes, even more complexity. It's particularly intended for very high definition, as we see this move towards ultra high definition TV. Interestingly, no special tools for interlaced video. So I guess as an industry, we're trying to get away from interlaced video. And the message here is, if you've got an interlaced signal, then de-interlace it first. We're not going to do anything special within the coder, just try to filter it and de-interlaced. But so it comes at a considerable price in terms of complexity, as I've mentioned. H.264 was controversial enough. In fact, at the time that H.264 was emerging, it was controversial to the point where some of the people involved in the MPEG committee were saying that, or had the view that there would never be enough processing power in one of these things to be able to do the decoding, let alone the encoding. Now, of course, it's easy. It's Moore's law just keeps on going, and H.264 is routinely used. We'll talk about the application areas in a minute. But HEVC, or H.265, took that complexity yet another stage, as you see. About twice the decoding load, but about 10 times the encoding load because of all these greater choices that had to be made. But I guess the good news is that it was structured to try to facilitate parallel processing to make it a bit more feasible. I have got a clip of some HEVC coded video, but I didn't set it up, so I'll show it a bit later if that's all right. But I wanted to, rather than just go through these lists of features in these two modern coders, I wanted to take a higher level view about the approach used in H.264 and H.265. And if you think about what was done in the earlier standards, MPEG-1, MPEG-2, H.263, what could we do to save more bits? You know, where were the restrictions? And there were two areas that stand out. I think if I gave you 5 minutes to sort of sit down and think about this, you'd come up with this conclusion as well. And one is that we don't really take much advantage of spatial redundancy within iPictures. So when we encode an iPicture in those earlier systems, it's essentially like a JPEG picture. We take advantage of correlation within each block, say 8 by 8 or whatever. But if we think about that picture as an example, you know, it would probably be good. You know, there's a lot of correlation between there and there. So why aren't we doing that prediction, for instance? You know, maybe this area predicting this area, something like that. So it wouldn't necessarily be a perfect prediction, but it could be better than just encoding each block separately. And what about larger scale structure, so larger than 8 by 8? It would be, just looking at this picture again as an example, why haven't we got a transform size like that up there, but you know, very small blocks down here? And so that was one of the approaches that was included in both of these systems, and it was just it's just a matter of extent. The H.265 just took the approach a bit further. So these more modern coders allowed prediction between blocks, allowed spatial domain predictions, and I'll illustrate each of these, and allowed for adaptivity of transform size. So instead of having this fixed transform size, we allow different size blocks. The other approach that, or the other area that stands out that we might be able to improve our coding efficiency is in terms of temporal redundancy. That is, when encoding P and B pictures. Because we've always in the past talked about this fixed block size. Right? We had a discussion about, is it good to have a large block size or is it good to have a small block size? Is there an optimum in between somewhere? And we said in the end, well, we're trying to balance the number of bits needed to encode all the motion vectors against the accuracy of our prediction. But that may be different in different parts of the picture. You'd agree? And so this was the other dimension, I suppose, that was utilised in these more modern coders. So let's just explore a couple of these in a bit more detail to explain what I was meaning. So there's this spatial domain intra-prediction. So spatial domain, meaning we stay in the pixel domain. We're not trying to predict transform coefficients. And it's encoder-assisted prediction. You'll see that it's a little bit like motion compensation, except we're talking within a frame. And the idea is that suppose we're encoding this particular picture as an eye picture, right? Intra-prediction, and we get up to this. Hang on. So we get up to that particular block. Now, we could do some, in terms of intra or prediction of that block from neighbouring blocks, all that we've discussed so far is just predicting the average intensity, right, the DC coefficient. But maybe we could do something about predicting the structure of that block using some encoder assistance. We can't be sure that that block, well, no, sure, I don't mean to be to use that term, sure. We can't be certain of any value when we predict it, but we couldn't really guess at encoder and decoder what would be the contents of that block. But if we tell it that this particular kind of vertical structure from up here continues down here. So if the encoder sends some side information, we might be able to predict it a bit more accurately. And so if we do that, then we can predict this one with a given bit of side information. Then we might go on and encode more parts of the picture. We get back to here, this one, then the larger scale structure might be in a slightly different direction. So we're, in particular, we're recognizing that a lot of pictures have edges and significant features that are roughly aligned in particular directions. And if we send some side information to explain how to predict that structure, so in this case again we do something relatively vertical, then it can assist our prediction. Prediction error is reduced, bitrate is reduced. So here, for instance, the encoder might tell the decoder just predict with the average, use the same average value as the surrounding pixels, and that would probably be a good prediction for that case. So how is the prediction done? Well, this is the solution in H.264. It allowed 8 prediction modes, but one of them is just the DC prediction, which is saying predict this block of pixels. We're talking about a 4x4 block in this case, based on assuming the pixel intensities are uniform. So in that case, you would use, I'm not sure if this is clear, but we're about to encode this block, right? We've already encoded these ones, right? So all of this information, all the capital A, B, C, D, E, F, G, H's and the capital I, J, K, L, I, J, K, L are already available at the decoder. They've already been sent. And we're about to encode the block lowercase a, b, c, d up to p. Okay, so we can use these, so we can either encode it as DC, so we just estimate all of these pixels based on the average of these neighbours, or we can predict that there is structure in a particular direction. So suppose, for instance, that there's some sort of an object, an edge or something, that's aligned more or less in that direction, just to illustrate it. Then the encoder would hopefully be able to recognize that that is most accurately predicted using prediction mode 7. Right? That's about the right angle. And so having chosen prediction mode 7, then both encoder and decoder have predefined algorithms that tell it how to predict pixel B and pixel E and pixel F based on the neighbours. Okay, so it doesn't have to come up with the prediction algorithm. All that the encoder has to tell the decoder is, I've decided that it's mode 7, and then both of them can look up the algorithm. So I've just chosen one to illustrate it, right? We're not going to go through all of them, there's no point. But if you expected structure in that diagonal, that vertical right prediction as they call it, mode 7, then you would expect that pixel A could best be predicted not by simply using, say, its closest neighbours A and capital I, but it would be better to have some sort of a combination of capital A, capital B, JKL, JKL, and actually leaving out I. Right? So the idea is to recognise that the dominant structure is in this diagonal direction. Both encoder and decoder make predictions based on this algorithm that's associated with the direction. Does the process make sense? Yes? Anyone not? Anyone confused? No? Okay. Right, so but it's encoder assisted, right? I need to emphasise this. So you could think of this as being a little bit analogous to the motion vector between frames, in that the encoder needs to tell the decoder, needs to give the decoder some assistance in generating its prediction. And exactly the same philosophy was used in the later generation coder, the H.265 or HEVC, but with lots more directions, as you see. 35 prediction modes for H.265. 9, not 8, sorry, were used in H.264. And this intra-coding mode is sufficiently efficient that it became the basis of this HEEC image format that I mentioned earlier. That's used at least by Apple. I'm not sure how widely it's used elsewhere. And it's considered to have about twice the efficiency of JPEG, in the sense that for a similar quality requires about half the file size. So it's quite an efficient means of doing this intra-prediction. This question I won't get you to answer, because it's a bit out of date now that I've just told you it's used in HEEC. So I was going to present this question to you to think about, if this intra-prediction is such a good thing, why isn't it used in still image coders like JPEG? Well, it just wasn't developed in the times of JPEG. And probably if it was thought of in the times of JPEG, maybe it even was in research papers, I'm not sure, it was too complicated. The JPEG standardization group was trying to balance the efficiency of compression against the processing and memory requirements to implement it. And we're talking the late 1980s, mid to late 1980s, I think, when JPEG was finalised, and processing power was a lot more modest, and memory was a lot more costly than it was today. So the answer to my question is, first of all, it's used in HEEC, but it also has been proposed in other formats. Google was proposing a still image format, which hasn't been widely adopted, but nevertheless it used this, some form of this intra-prediction. Okay, now the second dimension of our improvements, I'll go back just to remind you of where I'm at. So we talked about this one, right, improving our intra-prediction, or to take advantage of redundancy within the picture. The other thing we could do is look at improving the temporal the way we take advantage of temporal redundancy, and in particular freeing ourselves from this restriction of macro block sizes. So in H.264 there was allowance for splitting a macro block. So instead of being always 16 by 16, this 16 by 16 block, I imagine it was, is analysed by the encoder, and it decides that the motion that's being described across this whole 16 by 16 block is not uniform. And in fact, this part is moving in one direction, and this part might be moving in another direction. And so it decides it's better to split the picture up, the block up into two 16 by 8s, and then keep on splitting the lower half down, as you see. So there's this little hierarchy defined, and if the encoder wanted to, it can split it right down to 4 by 4 pixel blocks and associate a motion vector with each one. So the encoder has the responsibility to make this decision about whether we save so many bits as a result of the improved prediction that it's worth the overhead of sending the additional motion vectors. H.265 took this another step further. So H.264 had the macro block size selectable 16 by 16 down to 4 by 4. HEVC extended it even more to a quad tree partition that starts from 64 by 64 down, and it also allowed transforms from 32 by 32 down to 4 by 4. So a lot of adaptivity. As you see, The H.264 picture is allows for the different motion compensation blocks, but they are restricted to that range 16 by 16 here down to 4 by 4 here, or there's an example where it's split in part of the block. Can't see one. Anyway, and but over here in the HEVC case, we've gone from we're allowing 32 by 32 or 64 by 64. Looks like 32 by 32 down to the small size. And as I say, it's defined as this quad tree hierarchy. Okay, any questions on that? It's okay? Good. So this is where the additional coding efficiency comes from, in essence. I mean, there are other tools that are included, and we'll talk about the arithmetic coding in a second, but this is the main source of the improvements. So I thought I should just at least roughly describe this particular arithmetic coding approach, so we know at least broadly what arithmetic coding is all about. We encode sequences of symbols according to their grouped probability on this number line, but this arithmetic coding is a particular implementation of that, where it's described as context adaptive binary arithmetic coding, CABAC, and we can break that term down to understand what it means. Binary means that we're encoding just 0 and 1 words, so we're not using other symbols, not a wider alphabet. And it's context adaptive in the sense that as each bit is communicated, all the probabilities are adapted, so it can learn, in other words. So the process in flow chart form looks like this. So we've got all these quantities that need to be encoded, motion vector differences and transform coefficients and so on. They are assigned a digital code word, so binarized, so we might have a number of different possible values for our quantized transform coefficients, but each one is assigned a digital code word. Then it goes into the actual arithmetic coder, where it selects the probability model that applies. Depending on recent statistics, it decides for each bit what the probability of a 1 or a 0 is, and then applies the arithmetic coding. That defines the sub-ranges within that within the number length of 0 to 1, and sends off, or may send off a bit or a number of bits to the decoder at that point, the way that we discussed arithmetic coding earlier. But then it updates the probability model, the fact that these bits have been sent, and then this changes the probability next time round. So a fairly, as you might expect, a fairly complex form of arithmetic coding as well. So the upshot of all this is a significant increase in complexity. So this is a graphic I stole from this company presentation, but I think it summarises things reasonably well, even though the vertical scale isn't included. So there have been significant improvements in bitrate or coding efficiency over generations of coda, from H.261 to 263 to 264 to 265. It's oversimplified maybe, but it's effectively dropping by a factor of 2 in each case. But the price we pay is the significant increase in complexity. And this is why, I guess, I chose the H.261 model to look at in a bit more depth in terms of the process of deciding, do we encode a particular block, do we encode motion vectors, all this sort of stuff, and what's the sequence, rather than try to do it for here, because there are such a large number of options and possibilities. So as you see, the example highlighted there is that by the time we get to H.265, there are supposedly around 500 ways in which each macro block could be encoded. which is good for coding efficiency because you can potentially choose the one that gives the most efficient result, but bad for complexity because you need to somehow make decisions among 500 possibilities. And all of the decision making is outside the standard. Right? The standard is not going to say this is how you decide how to encode each block. This is how you decide to split macro blocks up from 64 by 64 into 32 by 32 or something else. Because, well, why not? Why doesn't the standard tell you that? Yeah, the decoder doesn't need to know. I mean, well, it doesn't need to make that decision. The decoder just does what it's told. When it's the encoder will tell the decoder this 64 by 64 block will be split up into this this quad tree form, and here are the motion vectors. Use them. That's what the decoder needs to know, and that's all that needs to be standardized to allow encoder and decoder to talk to one another. How you decide when to split up these blocks is up to you as a manufacturer. Nevertheless, H.265 is certainly used. I know it's used in Big Pond TV streaming. I'm not sure how widespread it is beyond, well, in other applications though. What's the performance? Well, here's a comparison with H.264 and MPEG-2, where just the fact that we don't have those rigid 16 by 16 macro blocks and 8 by 8 transform blocks means that the result of low rate compression for the H.264 coder is that the picture is basically a bit more blurry, but the block boundaries are not so visible, whereas it might not be visible to you. But in the case of low rate MPEG-2, this blocky appearance starts to be visible. Right. Okay, so there are some other coders that we should be aware of. I'm not going to, it might seem like I'm covering every possible coder, but there are a couple more that are significant and we should be aware of, so I'll go through those as well. Not just those that have been standardized by ITU and MPEG. So the next one I'll talk about briefly is WMV9. That's Windows Media Video 9. It's a little bit. There's a little bit of a story here. I'm not sure how interested you are in these historical stories, but anyway, Microsoft had this Windows Media Video coding solution, which was their proprietary coder. They used it in their products when they were doing streaming video. But they wanted it standardized. But the controversy was that they didn't come along to MPEG or didn't come along to ITU and say, can you have a look at this, guys? We've got some good ideas. Can you incorporate it in your coder? But instead they went along to the SMPTE, the Society of Motion Picture and Television Engineers. So this is a body that does standardize things in the television industry, but they have traditionally or historically had nothing to do with digital compression. They do things like defining picture formats for film and what would they do? Things like interlace processing and stuff like that. Things within television studios, I suppose, and things within motion picture studios. So, as I say, it was a little bit controversial that they went along to SMPTE, and SMPTE looked at it. I'm not sure that the extent to which they changed anything, but anyway, they gave it a stamp, and it is now in some way an international standard called VC1. And you know, Microsoft has been quite successful with this in that it is one of the formats that is supported on Blu-rays, for instance, as a result. This coder, in terms of the tools that are available, it has a lot in common with H.264, with a few differences. adaptive transform sizes. They allow even rectangular transform sizes. It's a little bit simpler in some respects. The slices are always contiguous in VC1. Remember I said H.264 allowed you to group the macro blocks from different parts of the screen. There's no CABAC, the arithmetic coding scheme. B-frames can be used for prediction for H.264, but not in VC1. And it's generally considered to be almost but not quite as efficient as H.264. But if you ask someone from Microsoft, they probably tell you, give you a different answer. But arguably, it's a little less complex because of these sorts of choices. Other significant video coders. Well, I would have, in fact, in last year, I would have given a bit more detail about some of these, but really, the ones that Google has been involved in have a historic role, but really have been bundled up. The technologies that they've used have been bundled up into the latest standard AV1, or the latest industry forum standard AV1 that I have mentioned briefly, and that's where we're going with this slide. So the motivation for some other coders has come from some organisations feeling that they do not want anything that's encumbered by patents. So even though, a bit of background about patents. So an organisation like MPEG is concerned with technical standardisation. It's not concerned with making money, at least not directly. So organisations can come along to MPEG, become part of the process of deciding what should be included in this next generation standard. MPEG or ITU, they work the same. And whether or not you have a patent on it, it might be included. And so we form the standard, and then at the same time they get together separately from the standard body and form, and it's just traditionally this is the way it's done, they form a patent pool. So if lots of organisations have a patent for different parts of a video coder, potentially if you as a manufacturer want to build it, you would have to go and negotiate with 10 different companies. So that's a bit of a barrier. So they form one organisation. So there's an organisation called MPEG-LA, Licensing Authority. So you go to MPEG-LA and you say, I want to build an MPEG coder. And they say, okay, these are the royalties you have to pay, and then they distribute the royalties to the patent holders. The system works reasonably well. So it's this MPEG-LA thing that makes the decisions about who has to pay how much royalties for what application. And to try to ensure that their standard is used, they have been pretty flexible about the licensing arrangements for H.264, for instance, in lots of applications. So unless you were a really big broadcaster with more than a certain number of customers, you didn't have to pay any rights. Nevertheless, a lot of companies still see it as a risk. They can always change that. They can always demand that royalties be paid whenever you use one of these patent encumbered coders. And so that's been a motivation for several companies, and Google is the most prominent, to release royalty-free coders. So coders that have slight variations on the tools that get around the patents, and so you never have to pay any royalties for them. Why would they be motivated to do that? Well, that's a topic of some debate, but in Google's case, it's generally considered if more people are using video more easily, they're using the web. If you're using the web, then you're using Google, and so you're seeing Google-placed ads. Okay, so Google first got involved in this area when they bought a quite successful video coding company
almost 10 years ago now. They paid $120 million for it, something like that, but then immediately just open sourced all the code. So by open sourcing, that means that yes, we might have the patents, but we're giving up our royalties. You're free to use them. And that was a coder called VP8 at the time. Then they have released VP9, another generation in which they attempted to compete with H.264 and H.265. It's well supported by browsers. It's used widely by YouTube, so it is used. But more recently, over the last few years, Google has been part of a significant industry forum, and I mentioned this group before, and their industry forums are coming and going all the time, and they don't necessarily have a big impact. But if you look at the names of the players here, you would think you need to at least take notice of them. So they've got Google, they've got Netflix, they've got Nvidia, Microsoft, Cisco, Apple has even joined, and they've come up with a specification for this AV1, which is a royalty-free coder, and it was released only last year. And it includes technical components from Google's latest generation. It was going to be VP10. It was only a prototype stage, but then it was bundled into this. And Mozilla was working on something, Cisco was working on something, and they put all the pieces together. So we'll see how successful this AV1 is. But it's worth remembering that when you're thinking which is the best coder, should I use a standards coder or a proprietary coder, or should I use a royalty-free coder, they are all based on that core method of interframe, motion compensated prediction, and block-based transform coding. Right? So that when I built up that model of a reference, what do I call it, basic video encoding architecture, they all match that. There's been no significant departure from that. At least not in the coders that are actually used, in serious applications. There are research papers that look at trying to apply wavelets in motion-compensated coders and stuff like that, but they haven't been widely adopted. Okay, so if they're all applying the same basic architecture and they're all limited by the same costs and availability of processing and memory, then the performance is not going to be radically different, you would think. So what are the features of this AV1 coder? It includes many of the tools we've talked about before. So the intra-prediction thing, some large number of angles. I think HEVC had 35, now AV1's gone to 56. It's a bit like claiming who's got the highest picture resolution on your phone. Anyway, they presumably believe that extra resolution is worth the overheads of specifying which of these prediction modes is used. There's synthetic film grain synthesis. So what does that mean? You'd be aware that in the cinema, even computer-generated imagery in the cinema, when it's actually projected, has this sort of noisy appearance of film grain, like when it was actually captured on film. Yeah, seen that? No. When you see a movie in the cinema, very rarely, if at all, do you see an absolutely perfect, even CGI surface without any noise on it. And it's a deliberate decision by the director or the movie production house to make it look film-like, because people are used to film that appearance. And so that's sufficiently required that they, in this coder, and there are other examples as well, they smooth out noise to try to make it easier to encode, but then they synthesize it at the decoder to bring it back. There's an arithmetic coder used, but it's not the Kavak one to avoid the patents. And it also attempts to detect what the camera behavior is so that it can help to predict motion vectors. But that's all I want to say about AV1. Maybe someone would like to investigate it more in one of the individual projects. Okay, so now I'd like to move on from... no, sorry, we've kind of talked about that, haven't we? Sorry, my contents list is not quite right, but let's just... I've talked about this at a high level. Let's talk in a little bit more detail about this decision about do I take a standard or do I take a proprietary solution. Technologically, as I said, there's no fundamental difference. These VP8, VP9, VP10, AV1 are all drawing on the MPEG-4 and H.264 and H.265 experience. And they're using the same basic architecture. Comparisons between performance of a standard particularly with a proprietary system is quite difficult because, as we've discussed, it depends on whose implementation of H.264 or H.265 we're using. There are all those decisions in the encoder that are outside the standard, so you have to have a particular reference implementation. So the comparisons are quite difficult. Proprietary systems and maybe something like AV1 may be able to be adapted more quickly just because it's easier to get agreements. If we're in the ISO, the International Standards Organization, then there's quite a bureaucratic procedure that's required to get agreement from all the member countries before you can modify a standard or add to it. But if you're changing something often, then that requires regular upgrades, and upgrading things is becoming more straightforward or more routine, but it can still be complicated for things like a set-top box or a smart TV, which may or may not be internet connected. The technologies are well known, as I said. Everyone's using essentially that same architecture of motion compensated, interframe predicted, transform coded video coding. It's really just a matter of parameter choices around that. Licensing conditions are usually comparable, except for those that are deliberately aiming to be royalty free. And it might not be the coder that's the most important choice when you're building a system. So the coder is just one component, and your choice might not be based on who can give me the absolutely lowest bit rate for a given quality. It might be that I need to integrate my encoder into my content management system, which is the one that keeps track of where the movies are, on which server, and what all the information is around it, or I need to integrate it with my digital rights management system, which does the piracy protection, and so on. Sorry, this is a little bit out of date. I didn't see this. AV1 will be finished soon. Well, in fact, it should be finished. It is finished. And there is a Chinese standard, AVS, which has been adopted on a widespread basis within China, which has performance comparable with some of these other standards, H.264 and H.265. Right. How are we going for time? Let's just discuss what we'd like to do tonight. Do you want to have another break at some stage, or push through? I'm not encouraging you to push through. I would be happy to have a break as well, but if you'd want me to just keep going, I'll keep on going. Anyone care? Sorry? You want a break? Okay. Well, why don't we stop here for 5 minutes? No more, and then we'll continue. And then we'll have about an hour to go. So it's probably a good time. Okay, so I threatened to show you some video examples, so let me do that. Just turn the lights off. So I'll show you two clips. This one here is, I'll just pause it, is, as you might guess from the title, it's AVC encoded, so AVC equals H.264, but it's encoded at over 6 megabits per second. And this kind of video with that sort of detailed background there is quite hard to encode, as you might assume from your knowledge of motion compensation, because there's a lot of detail there. And you'll see that, and there's also a lot of motion going on in the foreground here in the case of the basketball game. So we use up a lot of bits describing all this motion, and the background starts to get a little bit blurry. And you'll see that as we play that video. Right, so you see some of this background sort of going into focus and out of focus. You see that? I should just show that clip again. Right, there's something weird going on with that wall, I guess is what I'm basically trying to highlight. And I can contrast that with an HEVC version that's coded, same clip, same resolution, but coded at almost a third of the rate, 2.2 megabits per second, which on the whole looks a lot sharper. Right? You don't get those same artifacts. Well, sorry, they're still there, but they're not even quite so disturbing. So it's sometimes quite hard to demonstrate the difference between, or particularly a subtle difference between some of these coding schemes. But you know, for a third of the bit rate, it's quite impressive that the quality is certainly no less. Okay. I hope you could actually tell the difference from where you're sitting. No. Okay, what did we have before? But so, moving on from specific coders, you might be pleased to hear. I want to talk more generally about some aspects of controlling coder performance. In particular, what flexibility we have to improve the performance we get, given that we have some constraints due to standardization. And I showed this graphic before. So when we define a standard, as you'll remember, we need to define, well, that needs to define the interface between these two devices, and that really means that we're defining mostly what the decompression engine does, and to make sure that this buffer doesn't overflow and underflow, we're defining what that does. But there are other areas, other aspects of an encoder and a decoder that we could alter to try to differentiate our product. So if I'm building a TV set, for instance, yes, I have to accept H.264 or MPEG-2 coded video, but maybe I can do something clever on the filter, on the output, to make my picture look a little bit better than someone else's TV's picture. Or if I'm building the encoder that I sell to the TV studio, if I do something smarter about the rate control, which is deciding how many bits I can use, what's my budget of bits to use to encode this particular frame, and then the next frame, and then the next frame, Or I can do something clever on the filter on the input. I already alluded to this a little bit. Things like smoothing out noise to reduce the high frequency content and therefore save bits to encode the things that are really important in the picture. Then maybe my encoder is more attractive than someone else's encoder. And that's the intention, actually, in setting standards for only those things that need to be defined. The other block there is just in terms of network performance. If my decoder can cope better with errors and lost packets or similar, so I can, for instance, conceal the fact that any error has occurred at all in the first place, then again my decoder can be more attractive than someone else's. So what can we do to improve the performance given that we're using a particular encoder? So think of using any one that we've talked about. Say H.264 is very popular at the moment, so we're going to encode H.264, but how can I encode more efficiently than just the obvious thing of running my video through an encoder in real time? And well, one way that we can improve it is a process called multi-pass coding, and that is directly aimed at this. Just a second. At this rate control bit allocation thing, because I've got a continuously changing picture coming through here with different demands for bits. So how do I make this decision about how accurately or what quality or what quantization step size I should use for any particular part of any particular picture when I don't know what's coming next? So there might be this big scene change coming next, or a high action part of the picture, and I might need a lot of bits for it. So I want to make sure that I can allocate them in the most intelligent way. And one way to allow you to do that is if you know what's coming first, and you can know what's coming first if you do multi-pass. So we analyse the picture first. Of course, this is not something we can do on the fly for a live event, but if I'm about to encode a movie, if I'm Netflix, for instance, and I've got a latest release movie from one of the production houses, I'm about to load it on my servers, I don't need to do that in real time. So my encoder can go through this video and it can analyse it and can say, well, there's a low motion part, we don't need many bits for that. We need to save them for this bit because there's a moderate amount of motion here, and here we find there's a high amount of motion here. So if there's a high amount of motion, we need a lot of bits, so we'll try to save them a bit during here, and so on. And this type of approach is even used in home video editing systems. You might have, if anyone's been involved in doing that, they often allow you to tick a box to do multi-pass or two-pass coding to allow this analysis to be carried out before doing the actual encoding in a second pass. Is the motivation for this clear? Is it making sense? Yeah? Okay. Now, well, it would be nice to be able to do this live, but there's the obvious problem. We haven't got the whole program available to us to make these decisions about where to save bits and where we can use bits. But we can go part of the way there using a look-ahead technique. And this is actually used in high-performance television system studio encoders. So this is coding in real time, but we need to be clear about what real time is. Real time, or when we're doing broadcast TV, for instance, we don't need the displayed video to be just tens of milliseconds after it was captured on the camera. We can allow some modest delay. We can still handle live events, and we can still have interviews with journalists out in the field and so on. But if we can tolerate a delay of the order of a second or so, then we can potentially do some improve the efficiency of the encoding. So this is how it works, at least in one implementation. So the idea is that we have two encoder chips. Encoder chip number one is just fixed with this constant Q, constant step size, and generates compressed video, but we don't need it. This is dribbles out on the floor. It's just my metaphor. What we're interested in is the statistics of how many bits are generated for each video frame if we just kept the constant quantization step size. So we get some sort of relationship like this, and so this is telling us which part of the video requires more bits and which requires fewer bits. So as we're generating those statistics, we put the input signal through a delay of around half a second or so. That's about as much as we can tolerate before we do the actual encoding with the second encoder chip, and we utilize those statistics to perform our bit allocation and our rate control. So we haven't got the whole program, because it hasn't happened yet, over which we can decide to allocate bits, but at least we can look ahead for the next half a second or so, and if we see that there's about to be a spike in bits required because there's a scene change and there's a lot of action because it's a sports segment that's starting up or something like that, then we can save some bits for for some frames. We can drop the quality and accumulate a bit of some credit of the bits that we have available, and then use them when they're needed. Also make sense? Yeah? Okay. So it's the same principle as multipass coding. It just means that we have limited look-ahead capability. Another thing that we can do, as shown in this earlier diagram here, is here in the front end. If we can filter that input signal in some way, we might be able to generate a signal that is easier to encode, or, put another way, allows us to apply the bits that we have available, our bit budget, to the most important features of the image. So clever, intelligent pre-filtering is a way that we could potentially save bits and give greater performance overall. And this is the sort of thing that we might be able to do adaptively. The most obvious thing that would be useful to do is get rid of impulse noises. So by impulse noise, I mean isolated specks or single pixels that are significantly different to the neighbours. Now the assumption would be that that impulse noise genuinely is noise. It's not part of the picture. But again, from your appreciation of how image and video coding works, you would appreciate that to try to reproduce isolated pixels will require a lot of bits. Yeah, because the underlying assumption of our encoders is always that the picture has a fairly smooth structure and doesn't change radically across the picture and doesn't change radically from picture to picture, apart from scene changes and things that we can't avoid. So if there's an isolated pixel or an isolated, very small group of pixels, then if we filter them out, chances are it's not important in the picture, and we can save the bits that would be required to represent this feature that doesn't fit in our model anyway. We can try to do temporal filtering as well, so smoothing out things from one frame to the next, but we need to try to preserve edges, so we can't just do pixel averaging. We would try to do motion compensated filtering, so that we preserve edges. We actually filter objects as they move in some sort of trajectory across the scene. do filtering within a frame, even not even the apart from the impulse noise. Maybe we want to smooth out other noise as well, but it's labelled there in the dot point as nonlinear spatial filtering, and that's because we want to preserve edges. We always want to preserve edges if we can. We can smooth out the whole picture by just applying a Gaussian blur across the whole picture, but we're going to lose definition. But if we can intelligently filter the noisy kind of appearance, but preserve the main features of the image, then we're likely to be better off. We can also adaptively change resolution, for instance, if we want to. We could subsample if need be, if we're running out of pictures, running out of bits. But I wanted to illustrate that this filtering is not always, well, it doesn't always do exactly what you might expect. So don't worry too much about what these encoders are or the bit rates. It's just as much as anything a label. So this is a little segment out of a movie from many years ago. I can't remember what it was. One of those ones where it doesn't matter. People going to Mars. Anyway, I can't remember the title. Doesn't matter. But it's encoded in this particular case, as you see, with 2 megabit per second Windows Media. And Windows Media, so Windows Media Video, that WMV 9 that I mentioned earlier, does apply this adaptive filtering. But if you looked at that frame in isolation, you might think, well, it's not too bad. It seems to have preserved these edges, and the picture quality isn't too bad. So it's probably done a reasonable job, considering especially that it's encoding at a pretty low bit rate. But what's interesting is if you compare it with a higher quality version, this is 4 megabit per second MPEG-2. Again, I'm not doing a comparison between Windows Media and MPEG-2. They're operating at different bit rates. But what is interesting is that in this case, they've effectively shaved the guy, right? Because all of this stubble has been filtered out in this case, because the adaptive filters thought, oh, this is impulse noise. This is not part of the real picture. We'll just smooth it, and it'll be easier to code. And I'm sure it was easy to code, but we lost something from the original content. Got to get this right. Sorry, it's the only way I know how to get back to the right lighting level. Okay. So what do we do if we're running out of bits? If we've done our adaptive filtering and tried to get rid of noise, and we've done our look-ahead statistical analysis to try to allocate bits as best we can, but we're in some application where we're trying to reduce the bit rate to the point where if we just keep on throwing away or keep on compressing the data, then we end up with a terrible picture, something like this. And so at this point, we have to do something more drastic, and that's to either reduce the spatial resolution, to reduce the number of bits, pixels we're trying to represent, or reduce the frame rate, and that's what we do at very low rates. So some low-rate YouTube clips, for instance, will do this. So in the case of reducing the spatial resolution, of course, we would take the picture and subsample it, perhaps by a factor of 2 in each direction. So we've got a quarter of the pixels. The quality will, of course, not be as good when we, particularly if we blow it up to the same size. You know all about spatial frequency and the visibility of particular spatial frequencies. We can only represent lower spatial frequencies in this case than in this case. But if we've got a quarter of the pixels per image to encode, we could probably do a better job of them than if we consider the alternative, which might be this if we keep the full resolution. Okay, so it's a better trade-off to reduce the spatial resolution. Or if we continue to run out of bits, or if we're still running out of bits, we could also drop the frame rate. So instead of 25 frames per second, maybe we drop every second one, and we reduce it to 12.5 frames per second. Of course, the overall quality will not be as good. It'll be a little bit more jerky, particularly if there's a lot of action in the or change in the video. But the quality of each individual frame will be a lot better than if we have to encode twice as many.
So if we drop it to cloud vision, if will have visible flashes?
Sorry, these are the encoded frames, only 12.5 encoded frames per second, but then at the decoder we just duplicate, we just repeat. So we're not flashing at 12.5 frames per second. Good point though. Okay, so what are the factors from what we've talked about and from what we understand from the video coding discussions that will influence the picture quality at a given compression rate? What do you think? What are some of the variables that given if I'm given 5 megabits per second a bit budget, what will determine what sort of quality I get? Pardon? The quantization steps. Yes, but we can even be more general. I mean, the particular choice of encoder will be one. What about the signal? What would influence the quality we might get determined by the?
If it has high frequency or low frequency.
Yeah. So if there's high action or if there's high detail, yeah.
High motion.
Yep, high motion. So yes. What about the source of the signal?
So the source, maybe also the structure as well.
Yeah, I'm not sure if you're going to this, but whether it's interlaced or progressive, right? Because the interlacing has an influence. Remember, we talked about that one. Something that we were just trying to filter out. The film grain or noise. So it depends on how noisy that source is. If it's very clean, then we should get a better picture quality than if there's a lot of noise. We talked about the amount of detail and the action that's in that particular one. And you mentioned the quantizer step size, but really we can generalize that and say what's the encoder implementation. So not only which encoder are we using, but also whose encoder. Remember, if you're encoding or if you're building an encoder to standard, you have lots of choices. So how you actually implement the encoder is also going to make a difference. One of the other factors will be how long a delay can we accept. So if we have to have a very short delay because for instance, what's an example of, well, I'll ask you, what's an example of a video coding decoding system where we can, where we require a very short delay?
Live streaming.
Pardon?
Live streaming.
Live streaming. Well, yes. Qualified, yes. It depends on what we mean by live. I think we'll talk about this later, but
There's a type of the video.
sorry?
The type of the video.
Type of
The
Type of-
show.
yes, yeah. So is that kind of captured here, the amount of detail and motion, that's what, and the noise, maybe? But oh, I see. So in term, you were talking about delay. Yeah.
What's your synchronization?
Yeah, this is important, but why I'm saying there's a qualified yes for live streaming is if I'm watching say a news program that's live from a TV studio, if I receive it and view it 5 seconds after it's transmitted. Doesn't really matter. Even 10 seconds, 20 seconds maybe, I don't know.
Live sports.
Live sports, particularly not one type of sport, but how can I get you to? I can't think of the question to ask. But gambling, right? Racing. In fact, I'll come back to this, but this was a particular problem for Telstra that I was aware of when I was working there, because they were able to stream most sports with some delay of, say, tens of seconds before between the event and the display on the screen. But racing was a problem because people wanted to place their bets, and they wanted to place their bets at the last second after they see the horse in the stalls ready to go. But beyond, sorry, I was after another example of video encoding with short delay. There's a new or very recently emerged application, and that's video from drones. Right? If you're piloting a drone and you're piloting it according to the video from the camera that's coming back to you, that needs very short delay because otherwise you're going to crash. Right? But more generally, do you have enough time, or can you do non-real-time encoding? So can you do it in software that allows you to apply more choices in the different coding decisions you make, or allows you to analyse the entire video before you encode it, or do you have to do it in real time? And the other thing that we discussed very early on was the viewing conditions, right? So the size of the display is important. Are you encoding for a large screen UHD TV display, or are you encoding for display on a smartphone, on small size, or a tablet or something else? Here's a little illustration. I'll do it again. It's just so much easier to see. Sorry, when I turn the lights off. Just to illustrate the difference in coding artifacts when we have low motion and high motion, or different sources really. So here's as you see, a still from a static scene from the 2012 London Olympics. So first of all, it's a static scene because it's in the studio. The presenter may be moving a little bit, but probably not very much. All the background will be stationary, but also all the lighting is really good, and so there's very little noise. It's very easy to encode, and so the picture quality is excellent. But if we then look at another example, which is it's also a still from the 2012 London Olympics, but of course it comes from an outside broadcast camera where there was lots of motion. Actually, looks like it's in bright sunlight, but the lighting might not have been quite so well controlled. And because there's high action, the camera may have been panning. We're in that situation I was talking about earlier where we're running out of bits, and so you can see all these blocking artifacts, obviously, as a result. So just to illustrate this dependence on the type of picture that's input into your encoder, and particularly if you are doing the encoding in real time, so you don't have the opportunity to save bits for when you need them, to some extent. Okay. Is that the lighting we had before? Okay. Not expecting you to memorise this sort of stuff, but I'm just wanting to try to get across a few issues about the sort of performance you get and how it changes in this case with time. Encoder performance doesn't, or coding and decoding performance isn't static, isn't fixed once you agree on a standard. So, you know, as I say, the numbers aren't really important, but it's interesting to note on this plot that for a particular standard, so MPEG-2 became available in the mid-1990s, but sort of every year with improved experience and new algorithms to do the rate control and allocate bits and so on, the bit rate tends to drop for the same for the same quality for the target quality. Then we get a generational change where we switch over from MPEG-2 to H.264. There's a bit of a step change. The different plots are for depending on whether it's real time, whether it's interlaced, or whether it's non-real time and progressive. But then there's a step change when we get to the new encoder H.264, and then there's again a slow decrease in the rate that's used over time, and then there's another step change with the change of technology. But the bit rates do tend to continue to improve over time as the manufacturers gain this experience of how to use the algorithm, how to make all those decisions. And in fact, they need to do that, or else their customers, like the TV broadcasters, won't buy their coders. They essentially say, you've got to have a 10% improvement per year, or we won't buy any more encoders from you. What are the application areas that all of these encoders have been used in, or are still used in? I don't know that I'll want to go through all of these. Let's pick out a few relevant ones. In the video conferencing or video telephony or video calling area in general, H.261 is old, it's gone. H.263 is still used, but often H.264. H.264 has lots of different coding modes, including a low delay mode that can allow it to be used in that way. So I'm pretty sure that Skype uses H.264. For digital TV, that's not actually... yes, I think that is true. Yes. So in standard definition, for standard definition TV, at least here, this might not be correct for all countries, but throughout most of the history of digital TV, anyway, standard definition has been in MPEG-2. But with moves to high definition, MPEG-2 can do high definition, but at least here in Australia, the high definition channels tend to be H.264. So you might occasionally come across a television set that can receive the standard definition channels, but not the HD channels, and that's because it hasn't got H.264 decoding. And that's also the reason that the TV broadcasters tend to duplicate or simulcast those channels, so that even if you can't get the HD version, you can get the SD version. DVDs have been in MPEG-2, are still in MPEG-2. Blu-ray is a bit more interesting. So the standards for Blu-ray say that decoders must support MPEG-2, H.264 and VC1, the Microsoft encoder. But while early titles used MPEG-2, almost all of them in reality use H.264. We'll talk about digital cinema as a specific topic near the end of the semester. H.264 is generally used on most mobile TV applications, and for internet streaming there are a number of different solutions that are used, but there's been an overall move towards H.265 and now H.264 and now H.265, which are supported by HTML5, if you're familiar with the web authoring systems. And for IPTV, Internet Protocol TV, so things like I guess, Netflix and other streaming. Most of it has been H.264, a little bit of Microsoft's VC1, but there would be a move now to H.265 as well. The interesting thing to note, though, is the range of applications of this H.264 now being displaced by H.265, and who knows when what will happen with this AV1. Okay, so we've restricted our discussions to these broadly used coders and the well-defined motion compensated transform coding based coding methods. But I wanted to highlight three particular or different approaches before we finish with video coding and before we finish tonight. So, scalable coding. I've alluded to this before. The idea of scalable coding is that if we are delivering one video signal, or a video source I should say, to lots of different devices, say I'm providing a high definition version of television to some devices, and I'm providing a standard definition version to other devices, and maybe I want to do some internet streaming at the same time, so I'm delivering to tablets and I'm delivering to smartphones. Do I want to encode that my source video 4 times, 6 times, 8 times, or is there some more intelligent way? Right, so we're potentially delivering to different screen sizes, different processing capabilities, different quality requirements, and over different networks. And so the obvious way to do it is this, what's called simulcast, and so it's obvious in that all we do is take the source video and encode it multiple times with multiple encoders to get the best trade-off of quality and bit rate for each of our target bit rates. So what are the features of that? We have low overall efficiency because we're encoding lots of copies of the same thing. We've got a high processing load, so whether we're doing all those encodings in parallel or we're doing them in batch overnight or something like that, we've still got to do multiple encodings. We have to store all those different versions, and we have potentially lower network utilization in the sense that we might be sending the same video over the same common parts of our network, but they're in different formats to suit our different target rates or target resolutions. We also need to keep track of all those versions to make sure that we're sending the right one to the right device. And so these observations were the motivation for the development of an alternative approach. But it comes with its problems that we'll talk about in just a moment. So the idea of scalable coding is, of course, that we are able to represent a meaningful picture or sound from a subset of the total stream. So we would encode our video once, but we structure it in some hierarchical sense such that if we take the whole of the encoded bit stream, we get the maximum quality, highest resolution, highest frame rate, whatever. But if we pull off just a subset, the right subset obviously, then we're still able to decode the subset. So we have a lower rate, perhaps a lower resolution to suit a smaller screen, and a reduced bit rate so that we might have access over different networks and so on. And if we're broadcasting, then we need to broadcast just one version and allow the receiver to pull off that portion that it's interested in. So that's the principle. Right? Looked at another way, let's suppose we have we can have a low quality, low resolution kind of base level video representation or indeed image, to which we might add some more information to get a higher quality at that low resolution. Or we add more information and we are able to increase the resolution to a higher vertical and horizontal pixel density. And further information still, and we get the highest quality that we can at that resolution. The terminology that we use here is that the common one to all of them is called the base layer, and then we have then we have these enhancement layers that can be added to it to improve the quality, improve the resolution, and so on. There are different modes of scalability, video scalability. And we'll go through each of these sort of quickly. I'd like to get through all of them and finish tonight if we can. So we can have, for a given resolution, a given spatial resolution, given frame rate, we can have selectable quantization of the pixel values, for instance, to give a different level of quality, or different SNR as it's labelled here. We can have different spatial resolutions. We could have different temporal resolutions, different frame rates, for instance. Or we can do this thing that's called frequency scalability, but I won't bother trying to describe it before we get to the graphic. So let's just go through these quickly. So the principle of quality, or SNR scalability, is that we have our video that we encode using the DCT, for instance. We quantize the coefficients, we apply variable length coding, and our decoder over that far side, when it receives that information, it can decode and display that quality. But we also subtract the original, this base layer from the original signal, maybe it's after the DCT, and requantize the difference at a higher quality, so finer quantization, and transmit that as well. So this gives us our enhancement layer, right? So the idea would be that if a decoder only gets the base layer, it can decode and display at modest quality. But if it can get both layers, then it can add the finely quantized enhancement layer information to the original info and get a higher quality. So it's pretty high level. Does it make sense? Not sure?
That's the prediction.
No, it's not doing a prediction here. It's simply saying we've already encoded those DCT coefficients with a particular step size. Let's just subtract that from the original, so we have the error between that and this, and then we requantize it more finely. So we get in the end, when we add them back, we get a more accurate representation of each of the transform coefficients.
We did quantize 2 times.
Yeah. That's all right? Yeah. Okay. Yeah.
Why don't we just give the raw videos straight away go into the Q2? Why don't we
Because we want to allow for that possibility. Just a low rate version with lower quality that a particular set of decoders can still decode and display.
Yeah, I mean, the raw video can, we can give both Q1 and Q2, both the raw video. Why we need to go to Q1 minus 1 and then go into Q2? Do you know what I mean?
Well, I think I know what you mean, but maybe it's an implementational thing. But if this is quantizing our transform, if this is a uniform quantizer, for instance, that's quantizing our transform coefficients to, I don't know, 100 levels or something, we can't easily pick out the I'm not sure how we can pick out the a coarser representation of each of those 100 levels. Maybe we should talk about it later. Okay. So let's think of another dimension of this scalability. So there we were just adjusting the quality of the representation of each of the transform coefficients. Here we're saying let's start with a raw video of high spatial resolution, so say HD resolution. But to get our base layer, we downsample. Right? So we downsample to, say, standard definition resolution, more or less. Go through the encoding and decoding stage for that particular decoder. But again, subtract the low quality version from the, the low resolution version. We upconvert, compare with the original, and then where there's finer detail available, we recode those differences. So that in this configuration here, there's one decoder that just accepts the lower resolution picture and decodes it. Another decoder might accept both layers and combine them together to get the higher resolution decoding.
If we keep on adding these layers, enhancement layers,
Yeah.
will we get a better quality?
Yeah, that's right. Yes. So if we're only showing two enhancement layers, two layers, a base and one enhancement here, but we could keep on going if we wanted. Yes, and the more enhancement layers we have, the more quality we have. Interestingly, we can use exactly that same diagram and just change the label to temporal scalability, if you think about it, because what we can do is take a 25 hertz video, down convert to 12.5 hertz, encode and display that, up convert again, so we're sort of interpolating the the missing frames, take a difference and then to correct to the original and then encode that as an enhancement layer. So that down conversion and up conversion could be spatial or temporal. Okay, it means you kind of have to get your mind to do a jump about what's actually happening, but the diagram is the same. It just depends on whether we're talking about spatial resolution or temporal resolution. Okay, frequency scalability, the one I didn't describe earlier, and it's a little bit different in that all it's doing is separating out some the encoded information into two sets. So the idea here is that we have a conventional motion compensated DCT encoder. It's generating a set of data, and we just separate out the information that describes the first of all the structure of the picture in the first place, like where the picture boundaries are and which macro block we're talking about, and the low spatial frequency coefficients. But separate out the high spatial frequency coefficients into the enhancement layer. So the idea would be, as illustrated here, right? All the headers, the side information, the motion vectors, and the low spatial frequency components go into the base layer, which allows a lower quality version to be decoded. And then if we want the enhancement information to improve the picture quality, we include the high frequency coefficients as well. This is all very high level, I know, but I'm just wanting to get the concept across. And then I'm about to tell you why there's a problem, and then we'll finish for the night. So the features here, the naming, this is sometimes called data partitioning because that's what we're doing here. We're just splitting off our data into two partitions. Interestingly though, the encoding and decoding parts remain unchanged to what we used to. All it's doing is actually rearranging existing data instead of taking the differences as we did in the earlier stage. Now, the problem with scalability This is our concept. We've got this scalable encoder. We separate data out into a base layer and an enhancement layer. Let's just use one enhancement layer for now. In what we've talked about so far, I've waved my hands about quickly and shown you what we're doing, but I've ignored any prediction. Right? I've just said DCT, quantizer, variable length coding. If we add prediction, so we're predicting from one frame to the next, do we use the base layer or do we use all the layers to make the prediction? And we're going to look at both cases. And we need to remember that if there's to be, if we're to avoid problems in prediction, we need to make sure that the decoder makes the same prediction as the encoder. We've talked about that before. But our problem will be that some decoders may take one layer and some decoders might take multiple layers. So let's just think this through and discuss what should be used for this, this prediction loop. So here, let's suppose we just use the base layer for our prediction loop. So let's think of an example scalable encoder. What would be a good one to use? Let's say we're using spatial scalability. So the base layer is low resolution, and the enhancement layer takes us up to, say, HD resolution. And our prediction loop is, or the prediction data that we use to do our prediction is just using the base layer. So then let's think about what's happening at the what's happening at the encoder. The encoder isn't using any of the enhancement layer, that high resolution information, to do a prediction for the next frame. So the prediction won't be as good as it otherwise could be. Would you agree? So if we're not using the high resolution data to predict the next frame, we will have a larger prediction error than we would otherwise. Yeah? Okay. What happens at the decoders? This base layer decoder will be fine because it only takes the base layer information. The base layer information is used for the prediction, which it can do, and so it will decode and display a picture at a low resolution. All good. It will function, and it can make the same prediction as at the encoder. Same in this case, right? The full higher quality decoder takes the base layer information, uses the base layer information to do the prediction, adds the enhancement layer information that it receives, decodes, displays, and all is good. It's doing exactly the same thing as is done inside this scalable encoder because it's only using the prediction, the base layer for prediction. But the penalty we've paid here is that the encoding is not as efficient as it could be. As I said, we're not using the enhancement layer data when we're doing our prediction. So ordinarily our aim here, right up at this end here, I'm sorry. Yeah, right up here, our aim always from the point of view of coding efficiency is to make the best prediction here as we possibly can so that this signal here is small and this reduces the bit rate that we're sending out of the encoder. Here we're deliberately making a choice that limits the quality of this prediction because we're only using the base layer. So let's think about the alternative. So this architecture has no high frequency or high detail information used in the prediction, so we have loss of efficiency compared with a single layer coder. Now the alternative might be we can say, oh, okay, we want to improve our prediction, so we take as much information as we can about the encoded picture high resolution and low resolution included in the prediction loop, and we're making the same high quality prediction as we would if we were just doing a single layer encode. Then what happens at the base layer, the two decoders? Can anyone see where we're going? What's going to happen at the decoding end yet? I emphasise that the encoder is doing a prediction based on the base layer and the enhancement layer. So this guy can do the same thing, right? He's receiving the enhancement layer and the base layer, and performing the prediction. But what's going to happen to the other one, the base layer decoder? The prediction loops in the encoder and the decoder will be different now. Okay, the encoder is using the base and the enhancement layer for its prediction, and sending off prediction errors based on that prediction. But the base layer decoder isn't receiving that all of that error information. It can't create the same prediction as this guy. Okay. So the encoder and decoder will drift apart. Right? The base layer is. I haven't got a video to illustrate this. It's a lot of trouble to implement a combination that does this, but I'm hoping that you can imagine what's going to happen. So after the first frame, say, so we've got an eye picture, say, which both of them decode. There's no prediction involved. Then for the very next frame, this base layer decoder has slightly different information for its prediction than this one, because this one's using the high detail. And so it will, the reconstruction of the image on the output of the base layer will be a little bit different to what this one thinks it will be. And then the next frame will be the same, and the next frame will be the same. And so this base layer decoder output will drift. It'll be increasingly distorted from what this encoder is actually encoding. Does it make sense? Yeah.
So at the end of the prediction loop, do we get one set of motion vectors or two sets of motion vectors?
In the model I was describing, just one set of motion vectors. No, the enhancement layer, if we were using different resolutions, the enhancement layer would include a correction to the motion vector for the higher resolution.
Do we get a set of motion vector and just use the base layer?
Yes, because that's what the base layer decoder would use. Yeah. Okay, so the encoder and decoder, this encoder and that base layer decoder are going to drift apart, and it's the term is in fact drift. So, what's the answer to that? What will bring them back into synchronism? The next eye picture. Well done. Yes, that's right. So, whenever they're doing prediction over that sequence of whatever 10 frames or something, the base layer decoder will start to drift away, and then all of a sudden, ka-ching, it'll be brought back into sync by the eye picture, and then it'll start drifting away again. So we end up with this choice. Essentially, we have inefficiency, or we have this drift problem. When we make this scalable encoder efficient by using as much information as we can for the prediction, then some of the decoders will drift. We'll end up with a distorted output. If we restrict our prediction to only the base layer, then we get good compatibility with any decoder, but the encoding is not as efficient as it otherwise could be. So we essentially have this choice. It's very hard to avoid them both. I wonder if that's a fair question to ask you. Can you think of a situation in which we could take a subset of a coded video sequence without having a drift problem? Think of B pictures in MPEG-2 or MPEG-1 in particular. Remember, the problem is with the prediction.
Yeah, I think between the I and P, because we don't predict it.
No, the start of the sentence sounded really good. I liked the way it started. You just had to abandon it halfway through.
Because we use interpolating, I think, between I and C.
Well, if the B pictures aren't used to predict anything else, then it's not a problem in this case, right? So if we pull B pictures out and use them as an enhancement layer, the base layer will not drift, right? Because the base layer includes the I's and P's that are always predicted from one another anyway, so they're contained in that set. If we put the B pictures in the enhancement layer, then it's not a problem that some decoders won't receive them, right? Because they're not used for prediction anyway. But it's not necessarily a very good solution for coding if you throw away B pictures, because it reduces the frame rate and it means the whole picture is jerky.
They use B for prediction.
Yeah, that's why I said, think of it in terms of MPEG-2 type coding, because in H.264 you do use them for, or can use them for prediction. Okay, so we didn't quite finish this slide pack, but I've kept you till 8 o'clock, and you had a heavy start to the evening, so let's stop there, and we'll just finish off this these last couple of items, and then move on to audio next week. You'll be pleased to know we finally stopped talking about video coding for a little bit. I'll have your tests marked before next week, and there are a couple of people who haven't given me topics, haven't suggested topics for the project, so I'd like to hear from them, please. If anyone wants to talk to me about them now, let me know.
So I'm not quite sure why it will drift when we use the enhanced layer.
Okay.
Because
No. When we
do
the problem is
prediction.
this one, this base layer, because this guy here is doing prediction here that's using the enhancement layer, right? And the encoder is the encoded information that's being sent here is based on this difference signal, which is after prediction with the enhancement layer. So remember that the decoder is always supposed to be making the same prediction as the encoder, but this guy doesn't get this enhancement layer information either. Anyway, so you can't reproduce that step.
So the question I asked in the class, do we get just one set of motion vectors, so we cannot choose, because if you use some multiplexing means some here, we can make this several sets of motion vectors, so one of the sets just use the base layer, so that's not true. Yes, just get one set.
Okay.
You cannot choose.
But that sounds a bit like you're doing two separate encodings.
Yeah.
So,
But there's just one line here, so it's just one
so
group of motion vectors.
it sounds like it's
You cannot choose.
a little bit more like this, right? Isn't it?
Yeah. So that's not the case. We can just use one set of motion vectors.
Yeah, but I'm talking more generally than just motion vectors.
Which is predicted from these two
layers.
Yeah.
Yeah.
Okay.
That makes sense. Thank you.
I haven't maybe delved in that. That's the topic for this project. But augmented reality that I'm selecting, so you make quite a
Sorry?
augmented reality.
Oh, okay. In principle, what were you thinking to look at? The technologies of how it's done, or how it's put together, or
Yeah.
it's a very broad area, of course. So
You want some specific?
Oh, well, no, it's all right. I'm happy for you to go with augmented reality, but I think your first task will be to do a little bit of reading and see what you'll focus on, because it's a very broad area.
Yeah. Okay.
So you can
That's
refine
what
it
I
as you go.
That's what I was searching. I mean, the literature and the contents are there, so I just need to narrow down the.
Okay, yeah. If you could shoot me an email just to remind me, and I'll just make a record of what the topic is. Yeah.
So, but the topic will be
Yeah.
augmented reality.
Yeah, that's all. Okay, thanks.
I will mail you by tonight.
Yep, sure. No worries.
Hi. My question is about the project. So I think I already made my topic is the IoT.
Oh yeah.
My question is, so for our media content this subject, so first thing to know from what we see in the media, they're all belong to media, right?
Yeah.
What about the temperature we do heat color
Yeah.
and bright?
Yeah.
So are they still belong to the non-media?
In a general, in a like superset. Yeah, I think so. But we focus on audio and video.
Focus on that.
Yeah, we focus on that in this subject because they're the most demanding and also, of course, the most popular.
Correct. So
But if you have something in your project that looks more generally at other media,
yeah. So this is what I want to discuss with you is because I have some really study on IoT. IoT, is talking about to capture the data from everywhere, like sensor. A sensor can capture, maybe can capture the attention, or maybe they can capture the people's faces. So they are all they all can convert such thing into a kind of an information or data, and then display in front of the people. Right? So IoT can, like sense everything can capture data. So what? So I'm a bit confused. What should I look into to write this project? I'm not looking into the technology or what?
well, yeah, you can look at the technology, but I just would like it media oriented because I think there's a bit of a temptation, Internet of Things, we have lots of these things communicating. Well, how do the protocols manage it and stuff like that? But I don't want to know about network protocols. I want to know
Correct.
what's specific to the media. So, what I'd be looking at what are the applications that are enabled by this Internet of Media things. So the fact that we have all these sensors everywhere.
Yeah.
What are the new applications that media applications that are enabled?
To capture the thing or manage the media.
Or if you've got all this data,
Yeah.
what can you do in, I don't know, data visualization maybe?
What do you mean? What can we do?
Well, what's the
How
new,
can we use that?
what's the new capability that we have as a result of having all
If
these
in this case I have some idea because I learned something about the smart city or smart smart school or something.
Right.
So I got an example here. It's like for example for this classroom, right? And then we put a sensor somewhere outside. We can detect the brightness
Oh yeah.
of the outside running so big. So once because the sensor can send the data into our server or something, in any way to control or something, and then it can adjust the window to get some more bright or bright. It's kind of it's a opportunity. Do you want to see such thing? Or?
I suppose it could be seen as media. The other idea that comes to my mind is I don't know if you saw that thing I sent you. I sent on the discussion forum, a discussion board about what MPEG is doing. Yeah. Because they're doing something about Internet of Media things as well. So you might do a search to see what they're doing.
What's that? Big pad?
MPEG.
MPEG.
Like as in
Oh,
MPEG 1,
MPEG.
MPEG 2.
Yeah.
So I posted something on the discussion board saying that very brief description of some of the things they're working on now,
Yeah.
and one of them is Internet of Media Things. So Internet of Things, but particularly media ones, media versions. So
Okay.
you might look for some ideas from what they're doing.
Yeah. Okay. Yeah, because I hear maybe I took the wrong topic.
Well, it may be a difficult one, so, but
Yeah. So I just want to know what do you want to see from this IoT?
well, ideally, I guess I'd like to see, and this may not make sense, but I would expect something like Internet of Things enables all of these sensors.
Yeah, correct.
So that means that we can do this with video that we couldn't do before, or that means we can do this with audio that we couldn't do before. And
Or video or audio video.
yeah, or maybe it's the ambient lighting or something like that.
So you don't want to
And-
see how can we put this the ITO, how can we to make application or how
Yeah.
we use it?
Yeah,
So
yeah.
you don't want to see that.
I was about to say. So
Depends
what-
how.
Yeah. What is the new application that's enabled, and what are the new sort of technical parameters about it? So, does it mean that we've got thousands of sensors to create one image, and therefore there's this huge processing burden? And so, I mean, I'm trying to talk in the general sense, right?
Yeah.
But I'm trying to make an example of something that I don't really know. But as we talk about, say, video coding,
Yeah.
we talk about the fact that it has this motion compensation loop, and it requires lots of
Yeah.
processing,
Yeah.
and so you can, and there are different levels of complexity. Well, can you apply the same thing to a media application that's enabled by Internet of Things? I guess is what I'm asking.
Okay.
But have a look at the discussion board.
Okay,
Do a search on what MP is doing, because I'm sure there must be some documents that describe what they're
Okay.
doing,
Okay.
and that might give you some ideas.
Okay.
If you're nervous about the topic,